The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. This is Todd Han, and we're going to start right away here rather than waiting. It's noon. So to start out with, I'd like to thank everybody for joining the CLRA, Canadian Land Reclamation Association, Saskatchewan chapter, second webinar. And I'm actually quite pleased to introduce myself for this presentation. Again, my name is Todd Han. I am the senior biologist for Matrix Saskatchewan, and I have spent most of my career as an oil and gas regulator for those people who know me. And for a little over the last 5 years, I've been working as a remediation liability assessment professional, which has been quite a enjoyable work. So rather than waiting, I'm going to start right into the presentation as it is a fairly long one, and then I'll try to leave 5 minutes for questions at the end. So the presentation itself, we'll be talking about applying power of artificial intelligence to complete vegetation health assessment. Whoops. Yeah, sorry, folks. Let's see. There we go. To start out with, I'd like to start out with the acknowledgements. And a big acknowledgement to Dr. Kevin McCallum with the University of Regina, and also a colleague of mine with Matrix. He provided a lot of support, technical support, in terms of coding a lot of these softwares that we've been building. And also Saskatchewan Oil and Gas Orphan Fund, Saskatchewan Ministry of Energy and Resources, Torque Oil and Gas Limited, and Canadian Natural Resources Limited. They have been kind contributor, providing us with the interesting project that we can apply this technology. And of course, CLRA, Saskatchewan chapter, as well as CLRA, Canadian chapter, for giving us the venue to provide this presentation. And finally, my employer, Matrix Solution Inc., sponsoring this presentation. Now, before we start, I want to talk about the scope of my presentation. I don't want you to take away a wrong message in terms of the technology that I'm demonstrating through this presentation. So the artificial intelligence technology used in this presentation are really purpose-built. It's designed for vegetation health monitoring related to risk-managed problem sites. So sites that we know is contaminated, and sites that we work on for spill reclamation, and also those sites that require multi-year vegetation health monitoring prior to submission of detailed site assessment and acknowledgement reclamation. So we're dealing with sites that we actually have phase 2 environmental assessment data. Now, this demonstrated technology are not intended for use for terrestrial or aquatic plant speciation or identifying species at risk habitats or pre-development environmental assessment work or other types of ecological or vegetation surveys. That's not what this software was built for. In addition, this technology demonstrated do not replace the ground truth vegetation survey completed by competent professionals. Those are actually mandatory requirement, compulsory to carry out these machine learning image identification. And finally, the technology is really designed to enhance the ground truth data by leveraging the information that we get from a small ground truth data sample and be able to effectively leverage that into a much larger area that has the same ecological similarities. All right, so as we get in, I think the obvious question to ask is, why are you guys using AI technology when we have well-established traditional technologies such as Normalized Difference Vegetation Index, or NDVI for short? Now, for those people who aren't familiar with NDVI, it's a well-established technology used by NASA and other photogrammetric specialists. And it relies on fairly simple principle, in that if you have a healthy green vegetation, it's going to absorb most of the red lights and reflect very little visible red light. And then where it comes to near infrared spectrum, it absorbs half of the near infrared and then reflect the rest of it. Now, when you have an unhealthy vegetation, what happens is it now reflects much more visible red light. And then what you see is the yellow-red vegetation showing that it's not healthy. So this is a well-established technology. However, we're not using NDVI for one simple reason. The majority of the data, the UAV data and historical air photo data that we have lacks the near infrared spectrum information. So right off the bat, a lot of the data that we have that we can exploit do not have the piece of information that we need. Secondly, we can actually use a mathematical equation, and they call it false NDVI, to modify the color photos to kind of mimic NDVI. But what we found is when we did this, for some site it works, but for most of the site, this methodology does not work. For a simple fact that a lot of times the photo that was acquired were not flown during the peak season, so it might be early spring or late fall, and you don't have these green vegetations. As well, the combination that's involved in terms of trying to classify what the vegetation impact is using NDVI was difficult for the purpose that we were using it for. So we said we have to start exploring another technology. And where we arrived was machine learning. And so that you have some context in terms of how we started this, is this whole process started about 4 years ago. And then we're now able to show you some of the results. So back 4 years ago, when we were looking at machine learning, we were looking at the field of artificial intelligence. And just as a definition, artificial intelligence is intelligence exhibited by machines rather than human or other animals. Pretty simplistic definition. Now, machine learning itself is giving computer the ability to learn without being explicitly programmed. And when I saw that, I was excited because then I don't have to write thousands of lines of code. But as we got into machine learning, well, that wasn't the case. You do still have to write thousands of lines of code. So that out of the way, let's talk about the actual machine learning program or machine learning tools that are available to us. And there's two kinds that we'll be using and then demonstrating through this presentation. One is supervised, and within the supervised machine learning, we'll be using the classification. There's another machine learning which is quite attractive, called unsupervised machine learning. And in this case, really, it does not require any kind of training that we need to provide. And then it appears to be autonomous. And then the process that we use within that machine learning group is clustering. So when we get into the Vegetation Health Index classification, the question is, well, what are we trying to establish? And the objective of the vegetation health classification that we're carrying out is to use machine learning codes to scan a orthomosaic air photo, and that's just fancy word for stitch air photo that has one uniform coordinate system. And then we're trying to establish gross level vegetation growth expression. So what we mean by that is we want to know if the vegetation is growing or not growing because impact from contamination that may be introduced through the operation. We're not looking for subtleties as to say this area there's 88% growth and this other area has 86%. Those aren't the subtlety that we're looking for. We're looking for obvious differences, whether impact had taken place. Now, because of that, we keep the classes fairly simple. So the classification that we look for are bare earth, where nothing is growing, sparse growth, average growth, and then also we look for non-agricultural plants. Primarily, we're looking for weeds, and then shrubs and trees and wetland water courses, as well as human improvements. These are something that the computer can actually pick out fairly well, so we can classify those and have them identified through our scan. Now, there's two things that you have to realize. There are a lot of off-the-shelf software that you can buy that does the same thing, but they're fairly narrowly focused in terms of what they can do. So we needed a machine or codes that are fairly flexible, flexible enough to scan old vintage black and white air photos, but also scan multispectral satellite photos that we acquire from more modern satellite data. So that's why we decided to build our own. Now, as we were building it, we actually optimized our codes to work best for high resolution color raw photos from UAV. So these are, extremely high resolution that runs between 3 centimeter per pixel to 6 centimeters per pixel. So these are stuff that you'll be able to read license plates. Now, with machine learning, everything is really dependent on data, and the better quality data that you have, the better machine learning output that you're going to get. So it took us a number of years. It took just about 4 years to really design a UAV flight plan that optimizes acquiring the information that we need. So we optimize our flight for high overlap from back and forth and side to side with a low flight elevation so that we can get the highest resolution picture of the vegetation and the ground. We also take quite a care to put ground control points throughout the site, especially where we have things like a monitoring well that has geodetic ground elevation and coordinates. If we don't, then we use a fixed a monument to ensure that we have a proper coordinates attached to it. And the reason for it is we want to build a very accurate three-dimensional terrain model of the site, as well as a very high resolution vegetation coverage photo that's associated with the orthomosaic 2D picture that we use. Now, for purpose of these few slides that you'll see, I'm actually using a UAV flight that was taken in fall. And the reason for it is because it makes the illustration of how this technology works simple. Now, if I did not do it that way with a full summer data, it wouldn't make a lot of sense in terms of trying to illustrate it through a PowerPoint presentation. Now, it should be noted that you do not do vegetation assessment in late fall, so we do not recommend you do that. This is just for illustration purposes. So this is an example of an orthomosaic photo that we acquired from a low flight, high overlap. And we feed that into the computer as a color photo, raw data. Then the actual supervised machine learning training process is fairly simple. Once we have the photographic data, what we do is we provide a training polygon to the computer. And the way that's done is we have a competent professional who understands the site and the vegetation, and then provides a polygon, essentially a area location, and then provide certain data to that polygon saying that, look, you're looking at a tree in this case, or you might be looking at a water course. So we provide these polygons into the computer script, and the computer take this and then run it in multiple iteration to come out with the solutions or prediction of classification, and that's what you're seeing. So the computer comes out with the classification, and then in here we have 6 classes, bare earth shown in purple, sparse growth shown in red, and average growth shown in yellow. And then we also have shrub, tree, and the water course. Now the shrub and tree really was added not because we're going to get accurate data. It's fall, it's late fall, the leaves have fallen. But we needed to add that because if we left that alone, then we would have a null field, a field that has no data, so a computer would make up and fill that in with something. It might be black or it might be red, but it's not give us the wrong information. That's why these classifications were added in the training. Now there's one thing that we have to realize is it's not professional just looking at the air photo and eyeballing it and giving that classification or training polygon into the computer. There is actually a fairly rich set of ground data ground truth data that we get, and then that might be in a form of annotation, written words, or through photographs. And in this case, this is a photograph with annotation built in. The photo location that's taken is right here. All of the photos are geo-referenced, and then so we have exact coordinate, elevation, as well as a bearing, which direction that the photo was looking. And then you can see that the person who's providing the training polygon also has a ground level view of what they're looking at the air photo. And then this is the wide angle view of the terrain as well as the vegetation. But we ensure that they're also provided with other information, such as a close-up view in terms of what kind of vegetation we're looking at, what the health looks like. And then finally, we provide a quantification. So in this case, a square meter of area, and then there's a vegetation density count that occurs. So that we're providing kind of best information to the computer so that it has the best chance to give you the most accurate classification. Now, the other process that I talked about was the unsupervised machine learning. In this case, we just simply provide the color photo, we run the script, and the computer comes out with its own decision without having a training. And it does it by really looking at what are same and what are different, and then it groups those together in a cluster process. One thing that you should recognize is there is more classes when we do it this way, because there's a greater levels of subtlety in terms of differentiating similarity and differences. And we have to add more classes in order to differentiate those subtleties. The other thing is unsupervised machine learning at this point compared to supervised machine learning is less superior. In that supervised machine learning, we can actually check for accuracy by having ground photo data. For unsupervised, it's less so that we can do it because we're not controlling the training polygon that's being provided. Okay, so one other question that comes up is why are you doing it two ways? Why are you doing the supervised and unsupervised machine learning? The one reason that we're doing it this way is first, we want to improve the unsupervised machine learning at some point that it would be as accurate as supervised. But the other reason that we do it more immediately at this point is because we need something to compare. The issue with supervised machine learning, where humans are providing the training, it can introduce a human bias. And you may have heard this in the media that some of the facial recognition software have problem giving accurate recognition with specific racial groups. And then those might be because of either prejudice or some bias or generalization that's being introduced by humans. And we want to make sure that we reduce that bias as much as possible. And we do that through providing those ground truth photos to the trainer. But also, we can back end check whether the bias was introduced by looking at both supervised and unsupervised classification to see how close they are. And then we see that we do a precision test. One kind of test is within one spread of classification, just because the two learning method have different number of classification. Supervised has 6 and unsupervised have 8. So we allow for one spread. And then for those, we get precision about 78%. Now for exact match, we get 47%, but we can't have 100% exact match because there's just a different number of classification that occurs. So what this notionally tells us that we are not introducing, or we're minimizing the potential bias that could be introduced in this output. Now, what's really important is machine learning process, especially at this stage of the game for us, because we're at the beginning stage trying to develop this technology, is really dependent on um, how we're able to go back and then do some test, or go back and then see where the errors are. So in this case, the errors occur on these red dots. That's where our supervised and unsupervised do not match, and then white ones do match. Now I'm just going to switch over to a video here, and then hopefully this works. So the way we do this, whoops, oops. So the way we do this is we actually build a virtual environment of the terrain that you're looking at, and then the vegetation precision error. And what we do is we actually not only do it virtually, but we do it as an augmented reality. And this is an augmented reality system that we work with. And then what it does is it allows us to take this data, put it into a tablet, go out to the site and simply press your location finder, and it'll put you exactly where you are with respect to that data. And then this empty blue space will be filled with what the camera, the forward-looking camera sees. And then also you can click on those area that has error and then find exact coordinates and then what the problems are. Here, I didn't put the problem. I can go back to my presentation. All right, I hope that showed up okay. So we're able to now go back to the field and take pictures of where we get things wrong, and then come back and optimize and refine our codes so that we get it right as we move forward. Now, how do we apply this in a practical sense? So I'll show you a series of slides in terms of how this is applied in practical sense. So here we actually have a UAV photo that were taken at the right time. This is a summer of 2020 at a very high resolution at 3 centimeter. The one that you saw was 6 centimeters previously. And there's been a number of care taken in terms of collecting this data. So site itself is 1950 battery site with a well. And there was a flare pit, and then we know that there were pre-existing contamination, and primarily salt in this case. Now you saw how the training takes place, and then we can do a classification using the machine learning. Now this in itself is kind of useless, other than, Lee's site that hasn't been reclaimed is bare, great, and then there's some bare areas around the creek. So that alone as a data is, again, it doesn't really serve a lot of purpose other than you get a funny looking color photo. Now, what if we're able to go back in time and look at that site while it's operating and then see what the state of vegetation is? And then this is took quite a bit of work to be able to extract this information from black and white photo, and then of course using a lot of the more contemporary data, because we actually had 3 years of data for that site that you just saw with pictures taken in 2 seasons. And then we were able to calibrate our system to work with these older black and white photos. And then simply after a number of trial and tribulation, we were able to start extracting accurate information. So this is 1986 during operation with the flare pit operating. This is what the state of the environment was with the bare earth area being purple, and then the red being the sparse growth area. So that in itself was kind of neat. We can do that. But now the question is, how far can we kind of stretch that technology and see what the bleeding edge of the technology is, being able to make this useful? So what if we had an air photo before the development, before that site was ever built? And we did. This is, I believe, a 1959 photo, or I'm sorry, 1949 photo. And it's of pretty decent quality. And, we're just looking at a small snippet. The actual size of the photo that you've seen, including the color ones, are a quarter section level. What we were able to do is, from what we learned from 1986 photo, we were able to apply that refinement onto the 1949 photo before the development and figure out what the state of vegetation was. So when we put this together, we have the contemporary photo in 2020, and then also with the modern technology, we can actually build three-dimensional plumes, impact plumes, and then we can simply put that onto this site to show where our impacts are, in this case sodium chloride, respect to what the vegetation health looks like right now. And then we can add our 1915 or 1949 photo showing what the site looked like. Were there actually poor vegetation that pre-existed before these impacts were there? So that what that does is it let us really narrow our remediation strategy in terms of what we have to extract based on what the vegetation is doing at the site, rather than just looking at the chemistry. So I'll switch back. In a 2D, this isn't that spectacular, but if you can understand, this now is going to be built into a three-dimensional virtual environment, then it becomes a little more interesting. And I'll show you that environment. And this is that same site. And then I'm hoping this renders okay for you folks. You can see that we have a number of aspects. One is the existing flare pit, and then these lines are actually a drainage channel. And then these blue filled area is actually an area of flood risk. And the reason that we were able to measure it was we were quite fortunate that there was a beaver dam that was installed by our resident neighbors in 2019. And we were able to use that data to estimate flooding based on the water elevation rises. And then we can have our vegetation data, as you can see, but we can also start to look underneath that vegetation and then see the plume, how it's reacting with that vegetation. And as I have said, that being able to build a virtual environment working with the machine learning classification really helps us to understand that site better and then start to develop our remediation strategy a little better also. So now let's take this and then push that envelope even further to see what we can squeeze out of this technology that they call artificial intelligence. So we're going to have a little bit of fun with this. Before we start, I'll define what an artificial neural network is. So artificial neural network, or ANN for short, is a computing system designed to simulate the way human brain analyzes and processes information. It's kind of funny because I don't think we quite understand how human brain does actually work, but we'll go with this definition. It's a good one and explains how this system works. Now, what is it good at? Well, the ANN is extremely good at solving problems that would be proved to be impossible or difficult by human or statistical standard. So something that's really complex and has a lot of relationship, ANN is very good at solving those. So let's look at this candidate site that we're going to use as an example, because it's just kind of fun one, and I'll keep it as light as possible. So this is a 1958 well in southeast Saskatchewan. It's drilled into Frobisher Formation, and we were extremely lucky to have the produced water chemistry data. And what it showed for this site was the 1973 test showed that our sodium was about 10%, and the chloride concentration was about 17.6%. So it's highly saline water. And we have good amount of calcium and magnesium, but the great thing was sulfate was just about non-existent at 385 milligrams per liter. Just to put this in perspective, this is our site-produced water. Sodium chloride sits at 280 grams per liter, and if we compare that to Dead Sea, it's 250 grams per liter, and then there's a little reference to cup noodle soup at 9.2 gram per liter, and I'll show you how that relates to this presentation. So if we look at this overall site, it's just like a typical Southeast Saskatchewan site. We got 10-to-1 water cut, or even more in this case. So about 66,000 cubes of crude oil and about just under 800,000 cubic meters of produced water. Now, when we back calculate and then see what the total sodium chloride mass is associated with that produced water, what we see is about 220,000 tons of sodium chloride and about 300 tons of sulfate. Now, if we put a monetary value, according to 2008 salt export stat, and that was the most recent one I could find, we were selling a ton of salt for road de-icing for about 25 bucks a ton. So our site in its lifetime would have produced about $5.4 million worth of salt, with the idea that once you subtract the cost of evaporation and dehydration, you're going to lose any profit. So let's put this in even more realistic view on what this means. So I didn't realize this, but if we take the amount of sodium that was produced from this well, and then say if we use it to make cup instant noodle soup, we would make 24 billion cups of instant noodles. Now, one thing that I didn't realize is there's actually an association called the World Instant Noodle Association, WINA. I thought those are what we call people who eat a lot of instant noodle soup, but apparently not. In 2019, they reported that we, the planet, consume 290 million servings of instant noodle per day. So essentially, this well would have supplied 83 days worth of salt for noodle consumption. So just putting it into a kind of world view in terms of how much salt is being produced. Now, before we get into this site-specific, we'll talk about a little bit of the conceptual site model. There was a lot of work done at this site in terms of environmental investigation. And based on both borehole drilling, hydrogeological studies, geophysics, and the hydrology studies, we were able to eliminate almost all of the receptors, or eliminate the pathway to those receptors. So such as drinking water, potable water, aquifer, irrigation, livestock, etc., were all eliminated either by a study showing that pathway doesn't exist, or we're able to put a mitigation through engineered remediation system design that would cut off those pathways. The one thing that was conveniently left in this case was only receptor that would be impacted here was the agricultural crop. So let's dive into that a little bit deeper. So you saw in the previous slides that we can actually use modern technology to build three-dimensional impact plumes. So if we do that and start cutting slices from that three-dimensional plume, then we can get this table here. And it's essentially a tomography data. So we actually cut these thin slices at 10 centimeters, but I'm showing it as 50 centimeters just so that the table fits this slide. And within each of the slices, we can have information. We can have any information, but we can have information such as the average EC and SAR, mass of sodium, chloride, and sulfate, the area that's impacted, the volume, and the quantity of soil or mass of soil that's impacted. And then we can also sum that up for the rooting zone and the subsoil, also have grand totals. So what's important is this site, the impacted soil volume from these salt is about 74,000 cubic meters, or just north of $8 million if we're going to dig that out. And even for just the rooting zone, we're looking at a fairly substantive value, potentially hitting about $3 million to clean that up also. But let's look at this in a risk term. Well, what does it really mean? Because the 3D modeling can let us quantify the salt mass that's present at the site that was released, and it forms the impact plume. We were able to calculate that to be about 420 tons, and that equates to about 0.2% of the total sodium mass which was 220,000 tons, that was produced in the lifetime. So what it says is 99.8% of sodium chloride that was produced in association with that well was actually not released. It was injected or disposed of properly. Only 0.2% was released into the environment, intentionally or unintentionally. Now, in terms of risk term, what it says, so if you do that risk equation, the probability of release is minuscule. It's just nearly non-existent, 0.2%. But the consequences from that release are colossal. It's $8 million in this case, or north of that. So even a tiny bit of release is going to cause a lot of problem for these kind of sites. And unfortunately, this is not a unique site. This is what a typical vintage Southeast Saskatchewan light oil, crude oil production facility looks like. So anything that we can do is to optimize figuring out what the receptor impact is from the impact that's been released or contaminant that's been released, and be able to adjust the footprint in terms of our remediation will potentially save a lot of money and also have a smaller environmental impact with the greenhouse gas release or large excavation. So if we looked at in a say concentration term, obviously at 74,000 cubic meter, that's everything coming out. That chloride criteria is set at 120, and we already said that ecological receptors, aquatic life protection, those are all have been eliminated. So the 120 is out in this case. 250 is out also for the drinking water protection. So what we're left is these higher values that stretches from 1,000 to 10,000. So anytime we can pick a better concentration or higher concentration that has no impact to the only receptor and the pathway that exists at the site, there's going to be a substantive savings of between $1 million to $500,000 every time we move increment up in terms of that concentration. So let's go through that exercise and how we can come out with the kind of better figures on how we remediate this site or ultimately deal with this site. So you've seen this before. We take a site with a color photo that's been taken by UAV. We provide a training session, and we also do the unsupervised, of course. And then we come out with a classification. And here I'll simplify it. The purple area is a bare earth. There's very little pore growth. It's either growing or not growing. And the green area is the average growth, and yellow is just below average. And this blue kind of blank areas are actually water courses that exist at the site. They're intermittent sloughs and the intermittent water course. So what do we do with this? As we said, that this data by itself, machine learning image classification by itself, really doesn't render a lot of information or any value. But we can look at this data slightly differently for this site. We have significant information, environmental information, to tell us where the impact are, and it's been delineated. So this square area here are really the delineated impacted area. Now we can also set the same size area showing areas that are not impacted. Now obviously we have wells, and that you're saying, well, how can you say that? Well, there's a couple of ways. One is we either have chemistry data to show that there's no salinity, and other things are hydrology modeling, such as this is the surface water channel flow direction, and then we try to pick those areas that are upstream of our impacted area, so that there's no influences or potential impacted areas such as these well sites. So what do we get out of this? Well, we can extract the vegetation impact within those areas that we're looking at, the impacted and an area that would have low probability of impact. So that would be naturally occurring salt expression that's influencing the vegetation growth versus potentially man-made impact on the vegetation. And we can quantify that information. And then as you can see, our impacted area is shown on this first column with the bare earth expression of 17%. For the background area, what we did was some statistical analysis, came out with the 75th percentile confidence interval. And then when we look at it, our impacted area shows 17%, and our background area shows about 13%, showing that definitively there is a greater impact cause in the area where the well facility was operating. All the other factors are fairly similar, including the average growth. Now, we do take care that when we extract the information about the wetland, that we, again, normalize the data so that we're counting equal parts. It's not like, one area has a smaller cropland being used. So we make sure the ratio are exactly the same. Now, the other question is, well, Todd, there's obvious min-max here. Why don't you take it out? Well, I did want to take it out, but then there's only 4 areas. So if I take that out, I have no degrees of freedom. However, just for fun, here's what happens when you take out the min-max. And you'll see that the conclusion isn't different. It's just that the number do vary. So it just become more apparent that the bare earth expression is bigger. And poor growth and below average, really nothing to talk about. On the average side, yep, on the background, it performs a little bit better. But conclusion again, the impacted area have a noticeable man-made or human-made impact on the vegetation. All right, so what does that all mean in terms of trying to figure out how we can adjust our remediation to optimize it and get the best value? And one thing that we observed was in a general sense that if you have chloride concentration of 5,000 and high salinity, such as EC8 and SAR12, and that's shown in this red plume here, the probability of long-lasting and significant vegetation impact is high. And you're not going to grow a lot of crop in that area, or any crop. Now, for the area that's under 1,000 milligram per liter, and is shown in this blank area with no coloring, the probability of actually impact is very low, unless there is high naturally occurring sodium sulfate, in this case about 9,000 milligram per liter here. So the ambiguity exists between 5,000 and 1,000, which is shown in this blue area. And you can say, well, you can just run a linear regression and then find what the correlations are and come out with some kind of solution. And it actually doesn't work that way when we looked into the data. So if you look at this interface between this red plume and the blue area or aqua area, that's where 4,900 starts, and it should be bare, but it's not. It's actually supporting good growth. And then we have areas where it would be, let's say, 1,000 or just above 1,000, and we really have no growth. So what we're finding is there is no correlation that can be easily teased out through the system, and that we have to use another method. So what's really going on is, well, chloride or sodium chloride is not the only factor that impacts vegetation. Biology is complex, and there's a lot of factors that can influence it, and we can't just go measure chloride concentration and predict that there's going to be no crop growing, or go just measure sulfate concentration, or both, and then make that prediction. Life is just too complex to simplify it. So we know there's a lot of other influences, such as seasonal flooding that occurs and that carries some of these salts over, as well as the soil being underwater for a period of time because it's flooded, and also driving heavy equipment while the ground is soft and then causing compaction, the type of crop that's growing, the weather, how much rain we get, what the temperature was. So these all have a significant influence, even groundwater elevation that year. So how do we take all of these factors and then try to tease out some kind of prediction in terms of what may happen. So as I have said, artificial neural network is good at solving problems that are complex, that may be impossible for a human or statistical method. And then we said, okay, let's try to employ artificial neural network and then see if we can come out with the solution. So let me just explain how artificial neural networks in the most simplest term, because it's more complex than how I'm describing it, but this is about simplest I can make it for myself. Now there's three kind of layers. Input layer, where our independent variable, the stuff that we have data for, that we want to find out what the interactions are. So that might be things like SAREC, some of the cations and anion, and this says FLD is actually a flood risk elevation. Now, I'm not saying these are the ones that we're exactly using, but these are the obvious ones that you would use. We actually used many different and many more independent variables to actually run our test. Now, after that input layer, we have something called hidden layer. And this is like how your brain works. This is where you mull things and think about it and come out with some solutions after you do some matching and then correction. And then on the output layer is where you get the information or your prediction. Now imagine this: if I put a training data that has all of this salt information and flood elevation, but also what happened to the vegetation, whether it grew or not based on these parameters. And what computer does is it assigns a random value of weight, saying, oh, how important is this? Is SAR so important that we put a 90% random value that SAR is high, that nothing is going to grow? But that's assigned randomly. Then it does that for all of these other factors, and it goes through some kind of relationship, see how they are related together. Then it puts a data output saying, yes, something is growing or something's not growing. But in the training data, we know what the answer is. So it looks at whether it got it right or not. If it didn't get it right, then you would go back and adjust that random weighting that it first set, and you start to refine this. And if you do this 1,000 times or 10,000 times, or say 10 million times, which I'll show you an example of, what you do is you start to get it correct. You start to learn and then be able to predict things. And there's a set error limit, and once it hits that specification, then it stops doing this mulling over. So that's how basically ANN works. And again, this is fairly basic and probably a lot of errors in terms of explaining it. So what does it really look like? So what we do is we pick an area, and then this is the impacted area, and we put a bunch of queries, a gridded query, and we extract the information. So this is the SAREC, sodium chloride and sulfate flood elevation. And we tell it what happened. The vegetation, if it grew, it's 1. If it didn't grow, it's 0. And we take a bunch of rows of data. And in this case, there's 2,000, but you can make it 10,000. We ran 20,000, etc. And then computer now learns and figures out, okay, if these things happen, this is what the vegetation will do. And it has an error correction function, and we do the error check. And then also it has what they call confusion matrix. It looks at whether it's a positive or false negative or false positive. But essentially, it's basically learning on the examples that we provided. Then the next step is to give a test data. And then this is the area where we give all the same parameters, such as the salt numbers and the flood elevation, but we don't tell it what happened to the vegetation, because that's what we want the computer to solve. We want it to predict what's happening to that vegetation based on what it learned. Now, I'm kind of simplifying it, and what I'll do is, again, what's important is it's a data extraction infrastructure that's really important in terms of being able to do this effectively. I'm going to switch over to a virtual environment for you here. Now, this is how we actually do the test. We build this a full three-dimensional interface. Now, this is a representation of numerical data that sits in a SQL server. But we do it in a visual way because then we can easily just build a polygon and put a bunch of dots in there and start extracting data. And that's what this is. We have information about the surface, such as the flood elevation, the drainage, where the infrastructure was, where the vegetation impacts were, what kind of vegetation we have at the site. In this case, is soybean. And then also we have the subsurface data. And then you see these red plume, those are chloride. And then the gray and black are the sulfate and where they sit. And then we run a query, and that query essentially becomes a virtual borehole. And that's these virtual boreholes that you see here. And I'll turn it off and turn it on. And as it cuts through both surface and subsurface data, it logs all of the information that's attached to it. And then we're able to then go back and then get that into a tabular form as an output. Now, the reason that I'm explaining that is you have to have a platform to efficiently manage the data. Otherwise, these things take weeks and weeks to set up these tests. So by virtue of building that platform, we can do this now in hours rather than days and weeks. So what does it look like when you're doing this? So here's one of the examples. This is the most rudimentary example that we did with all of the independent variable put into a single hidden layer. So it's only mulling it over once. And what we get is accuracy of about 73% or error of 27%. Now, what's important is the type of error that it's creating. So this error here, where bare earth is what the machine learning image identification showed, but the artificial neural network says it's growing. And that's the one that we don't want. The reason for it is if we do not remediate an area that's bare because the artificial neural network says something is growing, then it's likely that the farmer is going to complain and we're going to have to revisit the site and spend twice as much money cleaning that site up because we missed it. Now, there's another kind of error where things are growing, but artificial neural network is predicting that it's bare. Now, we don't want this, but it's not as significantly bad as the other error. Now, we can make this more complex. I'll go with the two hidden layers with 3 neurons each. And then we see that we get an improvement generally, at 70% accuracy, 75% accuracy. But our error rate that we don't want really increases. So that wasn't very good. So we ran even more complex artificial neural network. And then we see that our total error, again, goes up. But the error that we're concerned about came down significantly from the last one. Then finally, we went a bit crazy here, added even more stuff, went with the 3 hidden layers. And then in this case, we actually ran, I believe, 80 million iteration. It took several days. Found out that just because you run it more brute force, it doesn't give you better results. So there's a scale of economy built in with this process. All right, so the results. So this is the result slide. And what it shows is these empty dots means we got everything accurate. The blue dot is an error where ANN predicts that it's bare, but there's something actually growing. And then the red dot is ANN predicts that there's something growing, but there's nothing growing. So let me just zoom in a bit. And then this is what a zoom in picture looks like. So the blue ones, again, the ANN predict that it should be bare, but things are growing. This is where our chloride might be 4,000, 4,500. But there's actually a good crop growth. And again, these empty dots means it got it right. These red dots, again, is bare earth, but ANN says there's something growing. And we think what's happening here, because just looking at it, there's something growing, is because we're using sub 3 centimeter resolution. It was like 2.2. It's seeing the gap between the crops, and then our dots are actually 2 centimeters. I illustrated much bigger here, but they're tiny pinpricks essentially. And they saw the gap, and that's why it identified it differently. Now, looking at the other side, we can see that where it's actually ANN got everything correct. But here we had some significant error rate that was occurring. And what happened was it was actually our error, not the computer error. We classified weeds, and that's a non-agricultural crop here, as bare earth, because it's just like bare earth. We're going to have to clean it up because we have a weed invasion. But we didn't set that up for the artificial neural network. So artificial neural network was seeing something growing. It doesn't care if it's a crop or weed. It knows something is growing. But our image recognition identified weed as bare earth. So that's something that we need to go back and refine it, and then hopefully get rid of that error. So we're just about at the end of the presentation. No, I'm not leaving a lot of time for questions. So in summary, I'm not going to tout this technology or try to sell you anything. Just want to point out some key facts and key things that we should be looking forward, kind of future looking. So based on this presentation, machine learning can replace time-consuming image recognition and vegetation health classification. And that's probably going to become norm, that we'll be using these technology more and more. Also, artificial neural network can provide some key insight to receptor impact on complex interaction between biology, geology, and chemistry. And we might be able to come out with a better remediation plan that provides better value. Finally, and I think this is an important point, the artificial intelligent tool is changing how we do our work. And I think we will be better served being proactive and be leader on how this technology will change our work rather than be followers, because certainly this can eliminate some of the current jobs that we're doing. So our focus should be creating formal training and education course in AI application for reclamation specialists, and also build open source application resource library. All the codes that we built, we took real care that it's an open source application or open source course code, other than a couple of 3D modeling. We need to start thinking about how we collect the data now, and it should be in a format that's seamlessly utilized by AI, because that's what's going to be looking at this data in the future. And finally, we need to develop a network that the professionals and academics can get together and share ideas and innovation. So that's it with my presentation. Here's my contact. If I can't answer your question in the next 2 minutes, please send me an email or send it to CLRA. And again, thank CLRA so much for letting me provide this presentation.
Awesome job, Todd. Do you want to try and field a couple questions? We got a few minutes here.
Yeah, for sure.
Sure. Okay. First question that popped up earlier in the presentation from Colby was, are you using both supervised and unsupervised machine learning for the VHI?
Yes, we are. Every site uses supervised and unsupervised. We always backcheck with unsupervised.
Okay. Another question, is this matrix's proprietary ANN? I guess maybe you addressed that by saying everything is open source, but maybe you can speak to that.
Yeah, so the codes rely on vast library of open source. So, you're not writing million lines of code. There are subroutines that are already written that we use, which are already open source. The only thing that would be proprietary to Matrix is actually the workflow and how we filter the data and how we build that platform to get the data. The coding isn't the hard part. The hard part is how you manage the data, because this is a data game. And right. Like I said, the codes are not proprietary. The workflow and the data management is proprietary.
Thank you for that. One more quick, or a couple more questions popping in here. Some of the soil properties, were they considered as variables such as fertility parameters, percent organic matter, nutrient deficiency, soil texture, etc.?
Yeah, that's an excellent point. And when I said the data that you were seeing aren't the ones that we're exclusively using, we also put in the lithology data, the fertility data, the groundwater data, temperature data. So there's a lot of things that I didn't show you, but there's a lot of data that does have a heavy influence in terms of your output. And then those are being teased out through experimentation. And they really do differ from site to site. Here we're growing soybean in southeast Saskatchewan, but if we're doing this in Lloydminster area, growing a different crop, we have to readjust the whole system and the training regime that would go into it.
Sure. We just had a couple more pop in here. What software package did you use for building the ANN? Would it be MATLAB or Python?
So right now we did it in R, but we'll be transitioning over to Python just so that we can integrate it with our other applications.
Sure. We'll rapid fire here a bit more. Any other applications of this technology? I mean, I'm sure that there's a million of them, but any that you perceive perhaps non-related to the environmental field?
Well, actually, I don't come from an environmental field. I'm a clinical microbiologist in molecular biology as a training. And I know for a fact that a lot of the stuff I borrow from them, especially on the health side with the cancer study. In fact, some of the codes that we use and the process that we use were from the groundbreaking work that Berkeley had done with cancer identification on cell level.
Okay, well, that's 1 o'clock here. I think we've put you through the ringer enough. For everybody who's interested in joining Saskatchewan CLRA, there's a discount code you can use for signing up. It's Hello SK 2021. So hopefully everybody will take advantage of that. It's 10% off the membership for this year. And thanks again to Todd for a brilliant presentation. It was something I'm definitely curious about, and I'm sure a lot of you, we had over 230 people on the presentation here today. So obviously there's lots of interest in it, and lots of thank yous coming in on the chat. So thanks again, Todd, and everybody. His email is listed down there. So if your question didn't get fielded, feel free to fire it off to him. He's a great guy, and I'm sure he'll be happy to answer it for you.
Thank you, everybody.
Okay, thanks. Take care, everyone. Stay safe.
All right. Well, I think I'm going to log out. Or did you guys need me to stay on?
No, I think we're good here. I think everyone's just kind of just logging off here.